So moving our story ahead a little bit here, we can actually get to the definition of the limit by acknowledging some of the work here. Pierre de Fermat, 1601 through 1665, did his work and basically laid the groundwork for Isaac Newton, who later came along and looked at Pierre's work and had an idea himself. He said, well, let's say we have some function, just some general function f of x, and we want to find a formula that yields the slope of the line tangent to the curve at any point x, not just at some point 2, 0, but any point along any curve. What could we do? Slightly restating the problem, we're actually asking you, what is the slope of the line tangent to a general curve y equals f of x at some point x, f of x? And as you can see, we have the same general problem right here. We have a coordinate point. We have a line that will be tangent to the curve. The question is, with only one point in hand, how can we find the slope of that line? So, like Fermat, Newton said, let's start with what we know. That is, let's start at the point x f of x, and then just choose some point h away from x, and let's see what happens if we let h tend towards 0. So we get this secant line through 2 points. We call it x of h plus f of x of h is the y values, x and y values here at this second point, x f of x from our first point. And if we do our slope formula for that and modify it down, we certainly get a formula that looks like this. And so he says, well, let's take the limit as h goes to 0, because that's essentially what Fermat did. He actually did it in a little bit of a different way than we do in our modern math, but essentially it's the same thing. He said, let's take the limit as h goes to 0 of this quantity and see what we can make of it. This limit right here, this limit of this difference quotient, which we've dealt with now a number of times, is the definition of the derivative. So the definition of the derivative says this. Let f of x be some function that is continuous over an interval that includes our value of x, where we want to find our slope. Then the derivative, we call it f prime of x, is defined as f prime of x equals the limit as h approaches 0 of the difference quotient f of x plus h minus f of x over h. And we can consider this our slope producing function derived from the function f of x. That's why we call it a derivative. All right, so let's figure out our derivative by this limit process for the function f of x equals 3x, or x squared minus 3x plus 2. Let's see what happens. So we've actually kind of dealt with this before, but let's go ahead and just put it all together in one piece here. So I'm going to bring up my pen. All right, and I want to say our derivative, f prime, I'll introduce you to some more notation here in a little bit. F prime of x, what would that be? Well, our derivative function is going to be equal to the limit as h approaches 0 of f of x plus h. Well, f of x is right here, so f of x plus h means that anywhere we see x, we're going to replace it with the quantity x plus h. So I'm going to get a big bracket right here to account for that. So I'm going to take 3 times the quantity x plus h squared. Oh, it's not 3 times. I see I'm already getting ahead of myself. It's just x plus h squared. Forgive me, minus 3 times the quantity x plus h plus 2 minus, and in this case we're going to just subtract away the original function x squared minus 3x plus 2. And all of that is going to be divided by h. So now we've got this big long expression to work out, but we're going to have to go through and deal with it directly as is. So we're still taking this limit. And I always encourage you to make sure that you put this limit notation in front of your quantity, just because it should serve as a handy reminder. We're always doing exactly the same thing in each step. And so this expression up here is only equal to this expression down here when these limits are put. So you want to make sure you put that in there. So this is x squared plus 2xh plus h squared when we square the quantity x plus h times x plus h. You can stop and verify that for yourself. As a matter of fact, I encourage you to do that right now. we're going to subtract away 3 times x minus 3 times h plus 2. And I'm going to distribute my negative sign into each of these terms right here. So I have minus x squared plus 3x minus 2 divided by h. Now, if we're clever enough, and really for these basic polynomial functions, hopefully we are, it turns out that whenever you do this kind of thing, mysteriously, these terms that are equal to, that have no h in them drop out. For instance, negative 3x and positive 3x will just add up to be 0. By the way, same thing with x squared and negative x squared, as well as plus 2 and minus 2. So look at what we're left with now. This quantity looks like 2xh plus h squared minus 3h all divided by h. And what's clever about this is that we get this limit as h approaches 0 of h times 2x plus h minus 3 divided by h. So h divides out and leaves us with a new limit as h approaches 0 of 2x plus h minus 3. And therefore, as we let h approach 0 by substitution, we can see that f prime of x, the derivative function, our slope-producing function, is 2x minus 3. And you ask yourself, oh, okay, that's all well and good. That's a nice slope-producing formula. But what good is that? Well, don't forget what our initial question was when we were looking at these, especially starting with from A, saying, well, what's the slope of a line tangent to a curve at some point x? Well, with this formula, I can say that, well, the slope of my line tangent to the curve at some point x, and we can pick any point x. Let's try x equals 1. At x equals 1, the slope of our tangent line right here, we now know to be 2 times 1 minus 3, which is to say negative 1. If we want to find out what it looks like at x equals 5, the slope of our tangent line there is now just very easily found as 2 times 5 minus 3, which is that we have a slope of 7 at that point. And we could go on, but in any case, this formula now has the ability to produce the slope of the line tangent to a curve at any point x that we want.